Let's do a quick refresher on what it means to be a subspace. Actually, I'm going to start with what it means to be a vector space. If I take a vector space, the way I know that it's a vector space is that it has things in it. Right? This is a collection of things. In this case, it's vectors. Um, and any two of those vectors, when you add them together, will fall back into this space. And if you scale one of the vectors in this space, it will fall back into this space as well. So that's how we know this is a vector space. That's what it means to be a vector space. A subspace, I'm using W here, a subspace of a vector space starts out by being a subset, right? So if you have here the collection of all vectors in R3, let's say. So this is R3. That's a vector space. If we take a subset of that collection of vectors, one such example might be all the vectors in R3 whose second component is 2, or all vectors in R3 whose first component is 0. So that would be a subset, but it's not necessarily a subspace unless it also satisfies these conditions. Is one of the elements in this set the 0 vector? If we are trying to show that W is a subspace of Rn, then it has to be. The 0 vector has to be in this subset, which means it was in the space to begin with, right? If it's in W and W is a subset of Rn, then the 0 vector must have been in Rn to begin with. So the 0 vector has to be in the subset. And then if I take two things in W and add them together, the sum has to fall back into W. That's what it means to be closed under addition. If I scale something in W, that has to fall back into W as well. If any of these three features is not satisfied, then W is not a subspace. W is only a subspace if and only if all three of these criteria are met. Okay, now that we've reviewed that, let's take a quick look back, I guess, at some of the properties of vector spaces. I've got Euclidean vector spaces highlighted here because that is where we're coming from. In chapter 5, we looked just at vector spaces where the vectors are made up just of real numbers. So again, as review, the properties of a vector space are that, again, with this notation, this is just shorthand notation, but I'll kind of go over it again quickly with you. This means for every u, v, and w. So for every vector that you find in that vector space, for every single u, v, and w, that means for all or for every. So no matter which of the three of these generic vectors I use in my properties down here, it's true of all of them, not just these three. And I can use any scalars that I want in the real numbers. So for any vector in the space and for any scalar, the following properties are true. When you add two vectors together, the result is another vector in that space, right? So you add two vectors together, you get another vector. Not only that, but if you add two n by 1 vectors together, you're going to get an n by 1 vector. So it's in the same space. That's what it means to be closed, by the way. The space is closed because when you do things to two things within that space, the result, another vector, still falls in that space, still ends up in that space. It's like it can't escape, right? So when you scale a vector that you find in Rn, it's still going to end up in Rn, so it's closed under scalar multiplication as well. Closed under addition and closed under scalar multiplication. The associative property says it doesn't matter what order you what order you add two vectors in, and it doesn't matter, the commutative property says it doesn't matter what order you add, whether you add these two first and then add the first to that result, or whether you add these two first and add the third one to that result. That's the associative property. You'll get the same thing. It doesn't matter whether you multiply two scalars together and then multiply your vector by that scalar, or whether you scale your vector and then scale it again. You'll get the same result. As long as a and b are the same numbers in both cases, you'll get the same thing. There's an identity element in the vector space, both for addition and for multiplication. In the case of addition, it's the 0 vector, right? I can take any vector, add the 0 vector, and it spits back out the vector I started with. In the case of scalar multiplication, there's an element, actually there shouldn't be an n here. There's a scalar in the real numbers, happens to be the number 1, that I can multiply any vector by, and in fact I can multiply it by either side, and I get back the vector that I started with. So we have an identity element for addition, and we have an identity element for multiplication, scalar multiplication. We also have an inverse element for addition. This symbol here means there exists, or there is, a thing out there called negative u in my vector space. It's already situated in my vector space, so that when I take a vector and I add this inverse vector to it, what it spits out is the identity, the additive identity. There is no multiplicative identity, because that would have to be in my vector space, and the things that I'm multiplying by are scalars, not vectors. So there is no identity. There's an identity, there's a scalar identity here, but there's no inverse. Sorry, I think I said there was no identity. There's no inverse that associated with multiplication the way there is with addition. And then we have 2 properties of distributivity. One says I can add together 2 vectors and then scale the result, or I can scale the individual vectors and then add them together, and I'll get the same thing. That's the distributive property. Let's see, that one's called the distributivity of scalars over vector addition. And this one is called the distributivity of vectors over scalar addition. And what this one says is I can add the scalars together first and then multiply them by the vector, or I can multiply the vector first by one scalar and then by the other, and then add them together, and I'll get the same thing. So that's just a quick review of the properties of Euclidean vector spaces. And why have I taken so much time to go over these? Well, because in section 6.1, we have exactly the same list of properties, except that now we're dealing with general vector spaces. So I have a few adjustments to make to my list, but it's not the list, it's not the properties themselves that I'm going to be adjusting. It's this stuff up here. I'll start by saying that in most cases we are going to be dealing with the real numbers as scalars, but we don't have to. We can take our scalars really from anything, as long as it's a field. And remember that we discussed the fact that the real numbers are a field, and so we can use the real numbers, or the real numbers may be the field that we're given to work with, but there are other fields out there as well. If it's not specified otherwise, you can assume that the field that you're working with, even if it's just labeled F, if they don't tell you this is the field of integers, or this is the field, well, integers aren't a field, this is the field of polynomials, for example. If that's not stated explicitly, then you can assume that the field that you're going to be working with is the real numbers. But instead of specifying the real numbers, we can just say, oh, it's a field, some field. So that is what this indication here means, is that when I say that let's see, how does your book say it? It's a vector space V over a field F. And that's what we mean here. When we say it's over a field F, it means that that's where we're going to be pulling our scalars from. Probably it's going to be the real numbers, but not necessarily. The next change I'm going to make is that the vector space that I'm working with is not necessarily Rn. I'm just going to call it V, because V is more generic, right? A vector space can be n-dimensional vectors, or it can be matrices, or it can be polynomials. It can be a lot of different things. Those are the ones that we're going to pretty much work with here. And so now I can say that this is properties not just of Euclidean vector spaces, but properties of vector spaces. I don't need that descriptor anymore, because these properties apply to all vector spaces. Now, your textbook actually labels this definition 6.1.2. It's defining vector spaces, a vector space V, and there's my V, a vector space V over a field F. What that means is that V is a set that satisfies these properties under 2 binary operations, addition and scalar multiplication. And then it goes on to say, let U, V, and W be in V, in the set V, in the vector space V, and A and B in some field F, then these are true. Actually, there is another change I could make here, that this is in the vector space, not in Rn, right? The Rn may be my vector space, but it may be something else. But whatever V is, if I keep finding them here, that is where these things live. And in fact, this is going to be an F. So a few more changes than I actually anticipated there, but all I've done is change Rn to V, so that I'm talking about any old vector space, not just Rn. And I've changed R, the real numbers, to F because I can be working with the real numbers, I could be working with that field, or I could be working with a different field altogether. Now a quick reminder, some of you, I'm trying to remember, in Calc 1, did we do summation notation? Is that Calc 1 or is that Calc 2? I think that's in Calc 1. But by way of reminder, I use this symbol here, which is the capital Greek letter sigma. Let's see, how do I want to, what kind of example do I want to give here? Let's just do this one for now. What this means is take this thing right here, this I, and start with 1 and go up to n, and what you're going to do in between is increment from 1 all the way up to n. So we have 1 and then 2 and then 3 and so on up to n. And specifically what this symbol means is that what you do with those numbers is add them together. So if I want to talk about something called P sub n, and I choose to define that like this, sum as I goes from 0 to n of a sub I x to the power of I, such that, or so that, or where a sub I is the element of some field, then what that means is, in a very concise way, a sub 0 x to the power of 0 plus a sub 1 x to the power of 1 plus a sub 2 x to the power of 2 plus, and so on, all the way up to a sub n x to the power of n. What's important to note here, this piece right here, is that these numbers here, the a's, right, those are coming from some field. Now, those might be real numbers. And in fact, for the moment, let's just assume that they are. What we have here is a polynomial, right? So let's see, a sub 0 could be anything. X to the power of 0, anything to the power of 0 is 1. So I can leave that x off. And then I have a sub 1 x to the power of 1. I don't need the 1 anymore. And after that, I do need to write my exponents. So I have some polynomial whose coefficients, where am I? Whose coefficients are elements from some field. Again, for the moment, you can assume that that's the real numbers, because I know that's where you'll be comfortable. This is just a concise way to write all of the polynomials with degree n. Right? Notice that they start with a degree of 0 and go up, just because of the way we're writing them. We could just as easily write this sum as a sub n x to the n plus all the way down to, actually, let's do a slightly better job here. Let's go with a sub 2 x squared plus a sub 1 x plus a sub 0 times x to the 0, which is 1. If I did do it in that order, though, it's conventional to write the first 2 or 3 terms, so really I should then have a sub n minus 1 x to the n minus 1 plus a sub n minus 2 plus x to the n minus 2. And as you can see, that gets cumbersome. And there's another indefinite number of terms in there. The dots are really too small. But my point is that, yes, I could start with the highest power and work my way down. But since convention dictates that I write the first 2 or sometimes 3 terms, by writing them with the lowest power first, I've avoided, writing all of this. I don't know. It's a little messier if you do it this way, a little more cumbersome. So I'm going to erase that just because we really don't need both. And I quite like the way it looks in the previous line. Now I've left something out, and that is kind of intentional because I really wanted to focus on what the summation notation meant. But what I've got here is, actually what I've got over here, this piece right here can be represented this way. But if I say P sub n is the set of, what I'm saying is that P sub n is a collection of all the polynomials of degree n or less. Because I'm taking my coefficients from a field, and because a field always contains an additive identity element, it always contains an element that acts like 0. And in fact, I said you could pretend this was the real numbers, or assume for the moment this was the real numbers. That means there's a number in here called 0. And these can always be 0, right? Any of these could be 0. In fact, all of them could be 0, in which case we have 0 times, 0 times x to the 0, 0 times x to the 1, 0 times x, and you add those all up and you just get 0. That is a polynomial. Well, that's not the focus of this video, but it is important to note that that is actually a polynomial. 0 is a polynomial. So, but my point here was that what I really need to do is kind of somehow continue to enclose these in brackets. In fact, let me just do the first one, and then I'll say everything that looks like this, such that a sub I comes from the field. So that I'm still representing a set, a collection. This is not just one polynomial, but all polynomials that look like this. Okay, all polynomials of degree n or less. So if P sub n is a collection of all polynomials of degree n or less, then the question is P sub n a vector space? The work that we need to do to figure out whether P sub n is a vector space is actually pretty chunky, but it's already in your textbook. So this example 6.1.2, set of all polynomials of degree less than or equal to n. So I'm going to leave that where it is. It turns out that it is a vector space over a field. The field could be the real numbers, could be something else, but it's already outlined in your textbook, right? That demonstration, it's not really a proof, but it's a demonstration. I guess it is a proof. It's a proof that P sub n is a vector space. It's already outlined in your textbook. So what I'm going to do now is I'm going to talk through how to determine whether a different set forms a vector space. Okay, here is another example. I'm going to let W be a collection or a set of all 2x2 symmetric matrices. Now, I don't think we've talked about what symmetric matrices are, but I'll just tell you here, this is just an example. So a symmetric matrix is one that's equal to its own transpose. So for example, if I had 1, 2, 3, 4, let's call that matrix A, then A transpose is going to be equal to 1, 2, 3, 4. So A is not a symmetric matrix, right? Because these two things are not equal. Notice that these two numbers, when you form a transpose, don't change. So it doesn't matter what goes in those two positions. What changes around is these two numbers here. And so if I want a matrix that's equal to its own transpose, then I'm going to need to, I think I'll just use the eraser, I'm going to need to make sure that these two numbers are the same, right? So whatever they are, I'm going to call them K. Now A is equal to its own transpose, no matter what K is. As long as K is the same, as long as both these numbers are the same number, it can be any number, right? So let me make one more change here. Let's change these two numbers so that they are more generic. We'll call them A and B. A and B. So now A and its transpose are the same matrix. So A is a symmetric matrix. So let's take A. I don't need this anymore. Let's take A, matrix A, equal to A, K, K, B. And we can say now with some confidence, with a great deal of confidence, that A is an element of the set W. A is contained in the collection of things called 2 by 2 symmetric matrices. And so what we're going to do now is check to see whether W is a subspace of all 2 by 2 matrices. And we're going to use matrix addition and matrix scalar multiplication to check that. So this is the question we're trying to answer. Is W a subspace of M? It's definitely a subset of M because W has 2 by 2 matrices in it. It has not all 2 by 2 matrices. It only has 2 by 2 matrices that are symmetric. But certainly it's made up of 2 by 2 matrices, and so everything that's in W is also in M. Not everything that's in M is necessarily in W, but W is definitely a subset. There are actually 4 things that we need to be able to demonstrate this. We need a set of vectors, a set of scalars, and 2 operations. And I've got most of those things outlined here. W, I've got the wrong pen, hang on. W is my set of vectors. Right, we're in a vector space here because it meets the criteria of a vector space. We have W is our set of vectors. We have matrix addition and scalar multiplication. Those are my 2 operations. So what I don't have is the set of scalars. I haven't identified the field here. And I can do that depending on the problem that I've been given to work with. It may be identified. But if it's not, we assume that it's the real numbers. So we can actually even write here, assume F is the set of all real numbers. That's going to make our work a lot easier because we know the real numbers. We're quite familiar with them. And in fact, we haven't worked with fields enough yet for me to be confident that you would necessarily be comfortable working with a different field. So I'm just going to stick with the real numbers for right now. What we want to do is show that any vector, any symmetric 2 by 2 matrix like this, when you add it to another one, will give you another vector that is a symmetric vector. That's another vector in W. And also that when you scale it, it will give you another symmetric vector or symmetric matrix. So let's start with A plus B. I suppose I'm kind of doing this on the fly here. And let B be equal to, now it has to have the same sort of features, the same properties. So let's call it CD. And, oh, I don't know, what should we use for our number that's the same in this case? How about P? It doesn't really matter. I could use L or Z. I could use X. I could use anything there. What matters is that for these to be symmetric, these 2 numbers have to be the same. Doesn't matter what they are. By making them different here, from here, I'm indicating that although this is symmetric and this is symmetric, they're not necessarily the same, the exact same number. Right? A and C could be different numbers. A and B could be different numbers. K and K must be the same number, but K and P might be different numbers. Okay, so if A is this matrix and B is this matrix, then A plus B by matrix addition is A plus C. K plus P, K plus P, and B plus D. And as you can see, these two numbers are the same. So it doesn't matter what these are. When I take, actually, let's do this. A plus B is that. And A plus B transpose is, I'm going to take this number, I'm going to take this row and make it this column. So A plus C, K plus P. And as you can see, do the same thing for this row here, that becomes that column. I get the same thing, K plus P, B plus D. So A plus B, that new matrix, is an element of W, which is the set of all 2 by 2 symmetric matrices. So even though these were generic values, when I take two matrices that have these properties, when I add two of them together, I get another matrix in W, another element of the set W. So that means that W is closed under addition over the field of R. So now we need to check for scalars. I'm writing this as a sentence. And I'm kind of building this as I go. This is good for you to see because I'm just kind of thinking on my feet here. When you read a description in a textbook, or when an instructor comes into the classroom and starts writing out a proof, oftentimes they've kind of thought through it, right? It's all very polished and perfect. Math isn't always polished and perfect. This is me kind of just putting this together as I go. Once it's done, you'll see it kind of reads like a more polished description, more polished explanation, but it's not always that way in one's head until it's actually on paper. All right, so I also need to know and let R be an element of big R, right? So I'm saying this little r is a real number. It's something in the set of real numbers. It's some real number. So then I can say that R times A is equal to R times A K K B, which by scalar multiplication gives me RA, RK, RK, RB. Put that in parentheses. And RA transpose is also, this row becomes this column, RA, RK, and then RK, RB. So RA is also in W. Therefore, another shorthand, therefore W is a subspace of M 2 by 2 or 2 comma 2. There are a couple of additional things we need to point out, and then I left those off in my haste to get to the meat of this explanation. I left these out. One is that the collection W, the subset W, is non-empty, right? There are some matrices in the set of all 2 by 2 matrices that are symmetric. So there's at least one thing in W. And that's part of our definition of what it means to be a subspace. W is a non-empty subspace of some other vector space. Okay, so we have that property I left out. Let me write that in somewhere. Okay, so I've added it up here. Note that W is non-empty. There's another one though. And that 0, we'll call it the 0 vector, equals 0, 0, 0, 0 is an element of W. All right, this is a symmetric 2 by 2 matrix. These two numbers are the same, and these two numbers can be whatever they want. If they're 0, then we have this thing that behaves like a 0, and that is another one of the requirements for being a subspace. So W is not empty. We can check that box. There's a 0 vector in W, so we can check that box. And then we can say A and B are these vectors. Notice how generic they are. If I add them together, I still get, I take this vector in A and this vector in B. I know I'm calling them vectors because they're in a vector space. I should call them matrices. Take this matrix in A, which is in W, and this matrix B, which is in W. When I add them together, my new matrix is also in W, so it's closed. W is closed under addition. If I do this scalar multiplication thing, I end up with another vector, another matrix in W, so W is closed under multiplication. And we say that it's closed under multiplication over the real numbers, over the field F, which is the real numbers. So this is an example of a different kind of vector space, a different kind of vector subspace than the ones that we've been working with.